Are we ready? So go Giants, of course. Woohoo! And go Cal Bears as long as they're at home. Yay! All right. So if you remember from last time, we started talking about demand paging mechanisms. And I had an interesting question afterwards, which I will clarify. The question was, I don't understand why demand paging is something different from all the stuff you talked about before. The way to think about what we're talking about now is that we showed you how the memory management unit works. We talked about what page table entries are. Demand paging is one thing you can do with the virtual memory unit. Okay, so that's what we're talking about. We're talking about treating DRAM as a cache on the disk. Okay? So in demand paging, the page table entry is crucial. And why is that crucial? Well, among other things, there's the valid bit, or if you're Intel, it's the presence bit. And what that tells us is whether or not the page is in memory. And the hardware can take over if there's hardware. So basically, a valid page table entry says that it is OK to let a request route all the way through to DRAM because that's a valid page. If it's marked invalid, that says you cannot allow the request to go through. Okay, simple as that. As you could imagine, valid, typically, the path is handled directly in hardware or mostly in hardware. Okay, so valid page table entries are things that the operating system doesn't normally have to take over with. Not valid is something where the hardware absolutely has to throw up its hands. It cannot handle that because the page isn't valid. All right, so at that point, the operating system has to take over. All right, are we clear on that? Okay, valid, hardware could do it. Not valid, operating system. Now, what happens when the user references the page with an invalid page table entry? Page fault. Okay? Memory management unit traps the OS, gives you a page fault. What happens on a page fault? Well, we were actually going through this last time. If there's many things that could happen on a page fault, but if specifically we're talking about demand paging in which we're treating memory as a cache on the disk, what we have to do on a page fault is pull the missing page off the disk. All right? Everybody with me on that? Secondly, we're going to assume that this page fault's occurring some long time into the execution. So in order to pull a page off the disk, we got to throw some other page out to disk. Everybody with me on that? Why? Because the memory's full. Okay? So this set of things here is all about kicking out one page and pulling in another page. And so notice the first thing we have to do is decide which page to replace. And then if it's modified, before we throw it out, we better write the data back to the disk. Because if we don't, we're going to lose some data. So that's why we check the D bit, the dirty bit. And then, in order to free that page up, we have to mark it as invalid so that the hardware won't use it anymore. Well, how do we mark it invalid? We set a page table entry to invalid. And then, why do I say that we have to invalidate the TLB for that entry? Why is that second half of number 3 there? Yeah. Remember when we hit the page fault, we saw it was valid. Basically, when we hit the page fault, presumably the PTA we're dealing with was invalid, but it's quite possible that this guy we kicked out was valid, so we better invalidate it. Then we load the new page into memory from the disk. We have to update the page table entry for that new page. Why? Well, it was invalid before. We're making it valid. We have to invalidate its TLB. Why? Well, because it was invalid before. We want it to be reloaded as valid. And at that point, after doing all of that, we can continue the thread where we left off, which literally means you return from the operating system and start executing at the load or store that failed. Okay? So this is the part that basically implements caching. Are there any questions on this? Yeah. So the reason we invalidate the TLB for the new entry is that it presumably was marked as invalid before, because that's why we got a page fault in the first place. Well, because you want to invalidate the actual TLB entry so it'll get reloaded from the page table, and now it'll say valid. Now, here's a good point at which to clarify something, all right? And I probably end up doing it by confusing you guys, but there's two types of valid here. There's valid in the page table entry, and then there's valid in the TLB. Can somebody explain to me how those two are different? Go for it.
All right, so the page table is a copy of, the TLB is a copy of the page table entry. So you need to make sure that the valid bit propagates to the TLB. Or if you invalidate, you need to make sure it propagates back. So there's one to cache the page table entries as opposed to being the application.
So I would say that the notion that one is a cached copy of the other one is not the two valid bits I'm talking about here. There's actually two completely different valid bits involved. Yes?
The TLB is a cache with its own valid bit in that cache, and then the page table is a DRAM, and it has its valid bit that your page table has.
So that's correct. The TLB is a cache on the page table. So the entries in the TLB are either valid or not, and valid or not means do they represent what's actually in the page table. Okay? The valid bit in the page table entry, we could, I suppose, to make this less confusing, always talk about it as the presence bit. Okay? But those are completely different bits. And that's why I talk about invalidating the TLB means kick it out of the TLB so that it'll get reloaded with the new page table entry. Okay? Yes, question in the back. Oh.
So since we already know the page table entry, why do we validate the TLB and not just update the TLB?
So why do we invalidate the TLB and not update the TLB? That's a great question. Anybody want to stab an answer? Yes. Okay. Want to stab at it?
It's expensive to transfer it back. So writing, you can just mask it and write the single bit. In this case, you would either write and read to propagate it back.
Yeah, so it's not because of expense. It's usually because the interface doesn't exist. So if you have a software TLB like in Nachos, yeah, you can update it any way you want. On the other hand, if it's a hardware-managed TLB MMU, usually they don't even give you that interface to update it. You can flush it, but you can't do anything else. Okay, good question. So, the TLB for the new thread gets loaded when the thread continues. And basically, if we're pulling a page off the disk, we don't want to hold up everybody else. So when we page fault, the process gets put to sleep. We start the disk activity. Somebody else gets to run. So later, when the disk page comes back, we can put that original faulting task or thread or process or whatever it is back on the ready queue. But we won't bother anybody else until that page comes back. Otherwise, we'd be wasting 1 million instructions worth of execution just to handle a page fault without anybody else running. Okay? Any other questions on this? This is sort of demand paging in a nutshell, all on one slide. Yeah? So the question is, when I say demand paging, am I very specifically meaning that an invalid page always means it's on the disk as opposed to the other things we talked about? Is that your question? Basically, demand paging is kind of this mechanism of getting a page on demand. I wouldn't say that demand paging is incompatible with these other cool things we talked about, like copy on write and zero fill and stuff. Usually you do both at the same time. And so I don't think I'll ever try to ask you a question that makes you come up with that distinction, because that would be kind of an unfair question. Okay, any other questions? Yeah?
For continuing the thread from the original faulting location,
Yep.
in a pipeline CPU, you could assume that when you faulting on like translating, like a decoding or translating the arguments, you would have the pipeline still be kind of full. How would you refill the pipeline, get to the point there?
Why don't you hold that question for about 2 slides? That's a great question. In fact, I'll even give a whole slide to that question. So how about another question that's not on a slide in 2 slides? I'm just giving you a hard time. No, I'll talk about that in a sec. Okay. So today we're going to talk about precise exceptions, which is exactly handling that question. And basically then, the hard part about demand paging is which pages do you kick out, surprisingly. And that's what we're going to talk about. So we'll talk about several replacement algorithms, and we'll talk about the clock algorithm and several others that you're used to. So before we get there, so MIPS, and by extension Nachos, has a software-loaded TLB. So what does that mean? That means that when you miss in the TLB, you got to go look in the page table. Now in a hardware-loaded TLB, that's all handled by the memory management unit. In a software-loaded TLB, you actually have to take a fault and go look up the page table to find the page table entry and then decide whether it's a page fault. So you actually get a TLB fault first and then potentially a page fault afterwards. Okay? Now, the nice thing about this is the hardware is simpler, and you can do any kind of page table you want because you're walking it in hardware. The downside is the expense is slightly there. And what you really hope is that you mostly hit in the TLB. You don't want to be trapping to software to do page lookups all the time. Otherwise, your performance is going to be very bad. Okay? So, how can we run without a hardware-filled TLB? If you think about it, the first time around, it seems impossible. How could that possibly work? And the answer is, well, it's not so bad. First of all, like I said, the fast path here is handled in hardware. So going to do a load or store that hits in the TLB, the hardware just translates it. You go directly to DRAM or memory or cache or wherever your lower levels are, and it just works in hardware. So the only thing we're really talking about, namely the slow path, is when it's not in the TLB already. So the slow path is either when the TLB hits, but the valid bit is 0 in the PTE, or their TLB is a miss. And at that point, we've got to do something which is typically called a TLB fault. Okay? And then the kernel figures out whether it actually had a page table entry loaded and turns it into a page fault. So usually we only have one type of fault here. It's not two. So what does the operating system do on a TLB fault? Well, first it walks through the page table to find the page table entry. If the result is valid, it loads it into the TLB, which notice the question Christos asked earlier. Here we can write the TLB. So if we have a software-loaded TLB, we can do anything we want, and we just plain load it in there. Otherwise, if it's not valid, we typically go ahead and call, kind of like a subroutine, the page fault handler. And that's exactly at that point as if we had hardware. And everything has to somehow be transparent to the user process. So it's busy executing its code. Whether we get a page fault or a TLB fault or whatever, the user code should never know the difference because we're trying to transparently cache. Okay? Good. Any questions on that? Now, the thing I still haven't answered here is, well, how does this all work out if you've got a pipeline and things are kind of half in flight and so on? That gets a little messy. So let's look at kind of a timeline here, right? So here's a case where the user program's running along, and at some point it executes a load or store, and that load or store misses in the TLB. So at that point we fault into the kernel, and we load the TLB by walking the page table. And presumably, if the PTE that we found got a valid bit matched, then what we do is we reload the TLB, and then we just start executing where we stopped. Okay, and basically we started instruction 1, and we want to re-execute that instruction. Why do we want to re-execute the faulting instruction? Can anybody guess? We execute a store, we get a TLB fault. Why do we want to re-execute the store? Or we execute a load, get a TLB fault, re-execute the load. Why is that? Yeah. Yeah. We tried, let's call it a load. We tried the load first. It wasn't in the TLB. We fault. The kernel runs. We go back. We rerun the load. At this point, it's in the TLB. And we continue. Okay? And notice that if we do that right, and the pipeline state's right, which I haven't told you about yet, this load never knows that we took this little T-tour into the kernel, except for the fact it's a little slower than it might have otherwise been. Okay? Now here's another example where faulting instruction number 2 It wasn't in the TLB, but by the time we looked it up in the page table, we discovered that the page table entry is actually marked invalid. And at that point, we know the page isn't in memory. So we couldn't do, here we were able to just update the TLB and keep going. In this case, we can't update the TLB. Well, we could, but it wouldn't help us any because the page table entry is invalid. So at that point, we go ahead and we start the process of loading from disk. And so these are not proportional. This guy is, millions of instructions. This one is much shorter. Okay? When we finally get the data updated, we can reload the TLB and now retry the load or store again, and it works. Okay? Does everybody see that timeline? Does that make sense? Okay, so in Nachos, you're actually going to be implementing these blue pieces, potentially. Okay. So we need to reload. We need to re-execute the instruction. Why? Well, we tried to do the load the first time. It failed. What does that mean? It means we didn't load. So our register is missing its value. So that's why we've got to restart it. Okay. And hardware here must really help out somehow. So for instance, this faulting instruction, we need to basically somehow save enough state here that we can restart. Okay, so for instance, we need to know which instruction caused the fault. Okay, why do we need to know which instruction caused the fault? Several reasons. Yeah. Which instruction to restart on? Okay, what else? Okay, that one may be a little too indirect, but the instruction address, we have to somehow know what the address was. Maybe if we know the instruction, we could compute the address in software, right? Okay, so somehow we need to know what caused the fault. Is it the case that a single instruction address, knowing which instruction faulted, is enough to restart? Yes? No, you say. Why? Okay, different processes will have different PCs. Yep. Right. Okay. Fortunately, so you're worried about the fact that we need to associate that PC with a process. Fortunately, when we do these faults, since interrupts are disabled, there isn't going to be any switching out from under us, so we know kind of which process is working. Well, if there's a page fault and it takes millions of cycles, what we're going to have done is unloaded this thread into a wait queue, put somebody else on there. And so, again, it will be OK if we re-enable things to run because it's a different process that's running than the one that faulted. Good. Is there any other reason that the single PC pointing at that instruction might not be enough? Yeah.
Generally, a load references registers.
Okay, load references registers, and?
So you need to know what the register value was, so you know what to address.
Yeah, so in general, we want to know what the registers are. The way to put that, though, is that we want to make sure that this fault handler saves and restores registers so that nothing gets screwed up when we restore. That's one when we start again. And also, we might decode the instruction in software to figure out what the address was. It's possible. OK. So the answer is hopefully, but I'll address that a little bit later about whether, in just a slide, as to whether a single PC is enough or not. You could imagine that if part of the state, if you have a pipeline and the instruction is kind of partially executed and other instructions are partially executed, and you stop the processor on a page fault, then what do you do to restart, right? I mean, do you have to save all that pipeline state? That's a question. And this is basically where this notion of precise exceptions comes into play. But clearly, somehow we have to save the PC. We have to save processor state so that when we get in here, we don't mess up things too much so that we can restart from scratch. And it depends on what kind of processor you've got, whether it saves and restores the registers or the stack, or whether the software does that. And the real question we're going to address here is what happens if the instruction has side effects. So let me just show you this a little bit. So what if an instruction has side effects? So a good example would be you go to do something, and as a result of starting, you've modified memory somehow or modified some other register, and now when you restart it, it's not idempotent. It's not like you can restart it multiple times because it's already changed the state. All right? And so basically, what we really want is when an instruction fails, we would like to back out of that instruction and everything after it in a way that allows us to purely restart from that one instruction. Okay, so think of this almost like a database transaction that's been flushed, or we talk about flushing the pipeline. So here's an example. I don't know if you've ever seen this assembly language syntax, but this says move. This is like a plus plus in C. This says move the value that's at the stack pointer into register 10, and at the same time increment the stack pointer when you're done. Okay, so this is kind of like a pop a single value, put the result in register 10, and automatically increment the stack pointer. Okay, so what happens if a page fault occurs when you go to either write or read from the stack pointer? Okay, actually this is a write in this case, but that's all right. Question: did it already increment the stack pointer or not before the page fault happened? Suppose it's already incremented the stack pointer, but then the page fault happens. Then what? What do? You have to undo the increment somehow, right? Because otherwise you can't restart from this address. Does everybody see the side effect problem here? You guys with me? What happens if we do this? String copy from one address to another. It's busy copying a long string, and there's page fault in the middle. Now what? Okay, there's a side effect because you've already copied half of the string. Okay, can you page fault in the middle and restart? No, right? Does everybody see that problem? So it turns out actually that what some processors have done is they go ahead and they force all the page faults that might occur in such a string copy beforehand, and then they pin the pages, and then the instruction runs. Okay, so that's one way to get around this problem. Okay, so what about more RISC-style processors? Here's an interesting thing. Branch not equal somewhere, load basically from the stack pointer into R1. What happens if that load page faults? Does anybody know about delayed branches? Who here knows what a delayed branch is? Okay, not too many of you. Did they talk about that in 61C? Okay, a little bit. So a delayed branch, here's a delayed branch. When you branch, you're branching somewhere, but the instruction afterwards always executes. Okay, so if the faulting instruction is in the delay slot, the problem is that if you restart at this load, what happens? Changes the semantics because we'll first execute the load, then we'll execute the instruction right after the load. But if we hadn't faulted, we would be executing somewhere after the load. Because it's a delayed, let me say that again. So a delayed branch, here, because of the pipeline, the instruction after the branch always executes. So when I go to branch somewhere, before it actually moves the PC to somewhere, it executes the load. So normal behavior is execute the branch, execute the load, then execute the first instruction at somewhere. Here, if I get a fault on the load and I restart at the load, I'm going to start executing from load, which is going to execute load, and then execute the next instruction after load, which is completely bogus, right? It's not at all what it was supposed to do. How do we fix that? How do we fix it? Hardware. What does that mean?
Put a flag when you're branching and make sure you run the load and then the branch again with nothing in the delay slot.
Okay. So we could somehow put a flag in here. So I actually suggest a solution here, which is what the Spark does. It actually has a faulting instruction actually has two program counters, the first one and the second one. Okay, so PC And NPC, when we fault at this load, we actually PC points at the load and NPC points at somewhere. So that's actually a case where the right state from a page fault is actually 2 PCs. Okay? What if I tell you that MIPS doesn't have a PC and an NPC? What does it do to fix this problem? Can anybody guess what an alternative would be? Yes. That's great. Yep. So when you fault on a load, before you start executing, you first back up one instruction. If it's a branch, you just plain re-execute the branch because they're idempotent. That's right. OK, good. So finally, go ahead.
So what happens if that load happens to change the state such that the branch not equals now is incorrect?
Well, but this branch, but the load, we'll talk about this in a second, is a precise load. So it actually, nothing is executed about the load.
So I mean, if you're loading R1, say the branch not equals using R1 as a compare comparison.
Right, but the fact that this faulted and you have a precise exception state means that R1 is not modified by the load because it faulted. OK. And then finally, a delayed exception. So let's take a look at this one. Here's a divide. Here's a load. Suppose the load is going to cause a page fault. The divide, however, takes 20 cycles to execute and eventually divides by 0. OK, now where do you restart that? There's 2 good answers to that. Where do you restart that code? Answer number 1. Yes? Good answer. You don't, okay, because it's a divide by 0. But if we've got floating point where divide by 0 becomes not a number and is an OK thing to do, how do you make this work? Where is the faulting PC here? Is it the load or the divide? Who thinks it's the divide? Okay, why divide?
Because load is that's the one that's faulting for the divide by 0, so you want to re-execute. But load, as you can see, the load R1 is from ST, then technically the load is not being affected by effectively or the division. Yeah, assuming that's the convention that it's loading into R1. R2 divided by R3 is R1, then you can ignore the.
Unless there's side effect flags that we're trying to get. Yeah. So basically, the bottom line here, and this is a lead into my final slide on this topic. The right place to stop is the divide, even though things happened out of order. The load page faults first, and then the divide divides by 0 later. We still want to figure out that the divide is where we've stopped making progress. OK? All right. So here's the notion of precise exceptions. And everybody ought to know what a precise exception is. So here we go. Ready? So it's the state of machine is preserved as if the program executed to the offending instruction. All previous instructions have completed the offending instruction, and all of the following instructions act as if they've never even started. OK? So these are the first 2 important pieces. OK? Does everybody understand that? So there is a precise exception is one which there is a single instruction. All previous instructions have completed that instruction, and nothing afterwards has even started. OK, now this precise exception is kind of difficult in the presence of pipelining. Why? Because we know we have a bunch of things going on in parallel. So how do we get a precise exception point when we've got pipelining? Yes? OK, we want to make sure that there's one point in the pipeline where each instruction commits back in the program order. OK, and if we ever have an exception, we want to flush out anything that hasn't hit its commit order yet. That's exactly right. OK? Any questions on preciseness? So fortunately, MIPS is a precise pipeline. OK, but fortunately, even more fortunately, since you don't get to see any effects of the pipeline, you don't have to worry about pipeline effects. But this is an important concept. Yes?
So you're saying you just kind of like let the processor just sit and do no-op the things that are halfway done finished?
So what you do if you get an exception is you need to make sure that things that are before the accepting instruction get to finish. And then everything from the accepting instruction on gets flushed out of the pipeline. And then if you do that, then you've got a precise exception point. And what's cool about precise exceptions is you can restart by just going to a single point. Okay? So imprecise means non-precise. Okay? And the problem with imprecise exceptions is system software usually has to figure it out. There is an infamous Motorola processor that was put into a whole bunch of printers, okay, called the 88110. And it had imprecise exceptions such that when an exception would happen, the operating system actually had to save pipeline state out. And then when it restarted, it had to store the pipeline state back in and then restart. It was a mess. Okay, so the operating systems designers hated that processor. Okay. So you can imagine that performance goals cause you to get rid of preciseness. Okay? And what are some good examples where preciseness might be okay to give up on? How about divide by 0, where it doesn't matter if you restart because you're going to kill the program anyway? Okay? What's kind of cool, and we wouldn't go into this now, but if you took 152, you'd find out that basically branch prediction and modern techniques for out-of-order execution give you precise exceptions for free. Because the whole part about out-of-order execution is you got to reassemble the instructions back in order later. And so basically, there is a buffer that's a commit buffer that recommits things back in order, and that gives us precise exceptions. Okay, I'm going to leave this topic now. Are there any questions on this? Okay, we good? So I would say most of the processors you're likely to run into today all have precise exceptions, which is kind of nice. The original mainframes and so on did not, and that was a really messy scenario. Okay. All right. Page faults, should they be precise or not? How many people think page faults should be precise? Okay, how many people think page faults could be imprecise? Okay, what about the rest of you guys? All right, let's try this again. How many people think page faults are should be precise? Okay, a few more of you. How many people think that they could be imprecise? Okay, so let's ask the people who think it could be imprecise. So what would you have to do with an imprecise page fault? Go ahead. Yeah, so somehow you'd have to figure out how to restart still, right? Now, page faults are definitely things where you want to restart. So I would say that precise page faults are by far the simplest thing for an operating system to ever deal with. Imprecise page faults are much less common. And there, again, it's the pain of restarting that tends to make people not want imprecise page faults. Okay. So what are the steps in handling a page fault? Okay, this is directly from your book. So basically, page is, we start somewhere over here. You do a load, and it faults. Because we look up in the page table, we see invalid. We get a trap. The operating system does what? It says, oh, page is on the disk. Okay, go get the page, bring back the missing page, and put it in a free frame. How did that become a free frame? Well, we looked for a free frame. We probably kicked something back out to disk. Once we've got a free frame, we fix the page table again, maybe flush the TLB. We restart the instruction. It tries the load again, and it succeeds the second time. Okay? So basically, when you're page faulting, you're potentially going through a very long path that involves a million instructions. So you don't want to page fault very often. Okay? So let's look at an example. So demand paging's like caching. So we could talk about the effective access time. So look at this. Effective access time, it's about appropriate around 5 o'clock today, right? Eat, is hit rate times hit time plus miss rate times miss time. This is the cache equation I showed you guys, right? Here's another version of it. Hit time plus miss rate times miss penalty. So let's plug some numbers in and see how important this is. Suppose the memory access time is 200 nanoseconds. Average page fault service time is, say, 8 milliseconds. P is probability of a miss, and 1 minus P is probability of hit. So let's plug some numbers in. So the effective access time is basically 200 nanoseconds plus P times 8 milliseconds. And if we normalize units, which if you're ever asked a question like this, make sure your units are constant across the whole equation, or you're likely to get a bad answer. You all learned about units, right? High school? Yes, units? OK, good. Let's plug some numbers. Suppose that one access out of 1,000 causes a page fault. The effective access time becomes 8.2 microseconds, which is a slowdown by a factor of 40. OK, so by having basically 0.1% page faults, we end up slowing everything down by a factor of 40. Do we want to have page faults? No. OK, if we have page faults, you're basically crawling. OK, and how many people have ever been in a scenario where they were page faulting a lot? OK, how do you know? The disk light's on and nothing's happening. OK, yeah, question or comment? OK. So what if we want the slowdown less than 10%? So you can use this equation backwards, right? And you see that the probability is basically 2.5 times 10 to the minus 6, or it's one page fault in 400,000. Okay, so in order to get no worse than 10% slowdown, we need to have no more than one page fault in 400,000 page accesses. So we better never page fault. And so that's why the replacement algorithm is so important, because if we load a page off the disk, we've done a huge amount of work. If we kick it out too early and then we go load it back again, we've just wasted a whole bunch of work. And so the replacement policy is the key. OK, yes, question?
What do you think about like these new MRAM technologies they're putting between the disk and DRAM?
So MRAM or flash, for that matter, phase change memory, these all have faster properties than disk, and they're non-volatile, so they will speed things up. But one way to look at them, most of the way people are using them, is they're a bigger cache. So what factors lead to misses? OK, so we'll talk about that in a second. Let's do some Administrivia just here. So still grading the midterms. We're hoping to give you them in section on Friday. There are already solutions up. I forgot to put that in the notes, but just go to the handouts page. They're there. I think you guys talked about problem 3 in section, right? So you went through that. OK. Turns out it's not a lot of code in the grand scheme of things. But I would say that's, if you don't quite understand problem 3, I'd stare at the solution a lot till you do, because that's a very canonical synchronization problem. You want an extra 5%? Yes? Come to class, ask questions, go to your sections. OK? Basically, we've got about a 5% participation grade, so it's good to make sure that you're participating and that people know who you are. OK. If we did the second midterm, which there are some who said they'd like to, and I've actually queried to see if I can get a room for it, it would have to be either the Monday or Wednesday after Thanksgiving. So I hear some neithers. Now, let me just point out one thing. So I know there were a couple of you that felt like you were, you bombed the midterm and that was awful. It's only 20% of the grade as it is, OK? The labs are 50%. Now, and the final is 25. Now, that's just the numbers that are kind of the layout, and there's a 5% participation. Now, if we did another midterm, what it would break down is 2 midterms would be 15, 15, and the final would be 15. So that would be the breakdown. So yes, no. How many people would like another midterm? Well, the problem is I need to schedule a room. How many people would definitely not like another midterm? All right, so it looks kind of 6½ of one, half a baker's dozen of the other. I suppose we could take the vote again. I need to, a recount, yeah. I need to figure out how to handle the topics if we're going to do a midterm on that, because I'll lose another day of lecture. But anybody don't care one way or another whether we have an extra midterm? 1, 2, 3, 4, 5. A few of you. Wow. Okay. So we also, by the way, have an anonymous feedback link if you don't want people to know who you are. Feel free to send us comments. We're actually going to have a survey soon, possibly this Friday if I get my act together, but maybe next Friday if I don't, about how you think the class is going and what you think could be done to improve. I know there have been some comments on some of the specs have been a little bit underdefined. We apologize. We're trying to fix those. But anyway, you know you can always come to office hours and talk to me about anything too. So feel free to do that. I had one term where there was a group of like 3 or 4 people that came to practically every office hour and talked about quantum computing and all sorts of weird things. So you're welcome to come and talk about anything you like. Project 2 is due tomorrow. So the term is really getting on. I don't know. Any other Administrivia questions that people have? So I'm getting a very conflicted class on having another midterm. From what I can see, it's about 50-50 split. Those who definitely don't want the midterm, would it scar you forever to have a midterm? Yes. Okay. All right. Especially not well, the problem is the Wednesday after Thanksgiving is actually our last official class. This is because they... Yeah, question.
No one really wants a midterm. It's probably just they got a bad grade. Or can we just skew the grade? If everybody gets really bad, can we just give them a little pat on the back? I mean, that's really what everyone wants.
I think I'll officially not respond to that question. Okay. All right, I'll take that under advisement. So, all right, let's go back to page faults here again, and then we'll take a break a little bit. But if we treat paging as caching, what factors lead to misses? Well, you already seen these, right? Compulsory misses. These are what? These are pages that have never been paged into memory before. So what's a good example of a compulsory miss opportunity? When might compulsory misses happen? Yeah. Yeah, starting a new program. What else? What are some other, okay, so we've got the text segment. What other segments are there? Yes? Context switch. Yeah, whether that's a compulsory miss or not, it's hard to say, but I'll give you that in that category. If it hasn't been running for a really long time, we context switch back in, maybe that's a compulsory miss. It's probably, yeah, that one's a little bit of a challenge, but I'll grant you that. Sure, what else? Yeah. Yeah, you allocate a huge array and you touch it the first time, right? These are all compulsory misses. And the way we might fix them is with prefetching. So when we talk about page policies, there are prefetch page policies that we can use to try to get around compulsory misses. Like when you start executing a program, if you get a page fault in the program, maybe you pull in the next 2 or 3 pages off disk. Seems like it makes a lot of sense, right? Capacity misses. Okay, not enough memory. So here we got to somehow increase the size of memory. I guess you turn the machine off and plug in more DRAM. Or that's not a quick fix, by the way. It's at least a trip to Fry's. What's another option? Well, it's interesting that there's increasing memory by reallocating it. You got one process that's got too much memory it's not using, and another one that's got not enough. You can shift the boundaries. Yeah, go ahead. So I would say we're already assuming we're doing demand paging, so the system's already leaving things on the disk that aren't being used. So these are kind of what happens over and above that. Conflict misses. So technically speaking, conflict misses don't happen in a page system. Why? Because we have fully associative cache. Why do we have a fully associative cache again? No. Why is the system looking fully associative? Yeah. Right, or any virtual address can map to any physical address in DRAM. Yes. So it's fully associative. So the final thing, which is kind of going to lead into the topic that we're going to close the lecture out with, is policy misses. And again, there was coherence misses and so on, but here in the OS, we're really going to focus on policy misses. And these are misses that are caused because a page was kicked out because of a bad policy. Okay? And how do we fix it? With a better replacement policy. Okay? Questions? Now you can see why we focus so heavily on this. Remember, we want one page fault every 400,000 accesses in order to avoid more than 10%. Okay, so this is really hard. Yes? So compulsory misses on the stack, yes, you'll get them at the very beginning, but the nice thing about the stack is you keep using the same pages over and over again, so your compulsory misses are going to disappear into the noise. Sure. Yeah. So in the case of the stack, you're right. You're allocating kernel memory, and so a miss is not as expensive in that case because you're just going into the kernel and its allocator is grabbing a free page and putting it into your page table. Yes. So compulsory misses initially on the stack aren't too bad, but once you start writing data, then if your stack happens to get kicked out, then it's going to be expensive, but then of course it won't be compulsory anymore. So you're right. I'd buy that. All right, any other questions? Okay. So what are our replacement policies? So replacement's an issue with any cache. We said with hardware caches, it's probably LRU or random. It's really important with pages. And the reason it's really important is because the cost of being wrong is so high. If you kick something out that you're going to need later, you've done a bad thing. Okay? Now, here's some options. What about FIFO? So FIFO says you take the oldest, you mark the pages by how long they've been in memory, you throw out the oldest page, and you're really being fair because you basically let every page live in memory for the same amount of time. Okay, so you can imagine taking all of the physical pages and you just walk them. You say, I'm going to replace this one, this one, this one, this one, this one. And you walk your way down, and then you come to the next back again. You're basically replacing first in, first out. Okay? Good or bad policy? Okay, well, it says bad on the screen. Think about this for a second. It basically throws out heavily used pages because it doesn't discriminate between a page that's used a lot and a page that's not used more than once. Right? Because you use a page once, gets loaded into memory, and it's going to stay there until you go all the way around and come back. It doesn't matter whether you used it again. On the other hand, if you use a page a lot, it's only going to stay there until you come around back, at which point it gets kicked out. So there's no discrimination in the FIFO policy between pages you need and pages you don't. Okay? It's certainly simple. That's what it's got going for it. By the way, you do see a pattern here on FIFO, right? FIFO scheduling policy. Well, it's simple. FIFO paging policy. Well, it's simple. You can see that basically FIFO just doesn't cut it usually, but we usually use it because it's a good thing to a base case. Here's a better base case. We call this min. And this is replace a page that won't be used for the longest time in the future. Okay? This is like an oracle, exactly. So this is the oracle, and it's really great, except it's not quite real. But we can certainly use this as a base case in simulation. Okay, right? We could basically simulate, see which page is the farthest in the future, and then do a replacement policy based on that. Okay? Here is another option. Here's our friend, random. Now remember, we had random in the hardware case, which we actually said was pretty good. Remember that? I said random's not too bad in the hardware case. Random here is not so good. And the reason is it's very unpredictable. And if you kick a page out one time, you could have a huge hit. And if you don't kick it out the next time, you have no hit. And so your runtime of your program is going to be completely unpredictable. And you won't know whether it's good or bad. And it's also based on zero information, right? There's no information about whether a page is heavily used or not. Okay? So, what have I missed here that might be a good policy that's neither FIFO, unimplementable, or random? What's another obvious one we could do? LRU. Okay, why might we think LRU is a good thing? You guys are with it. Good. Why might LRU be a good thing? Yeah.
It's almost FIFO, but it at least refreshes things you access multiple times.
Okay. I'd actually say that LRU is much better than FIFO under most circumstances. But what we'd like, go ahead.
It approximates min.
Okay, it approximates min. How?
Like say chances are if a page is being used very often, then it will be used again very often. And otherwise, at tiny lapses, it just
Yeah, so least recently used, if we can really figure out which page was used farthest in the past, it's likely to be used farthest in the future, right? Because the things that we're using a lot, we're going to use soon. Yes?
Is min provably optimal?
Depending on what your criteria are, yeah, min's another one of those provably optimal policies. So LRU, of course, is a good one to think about. And this is basically, it's a statement that programs have locality, and therefore it's useful to use your locality of access to try to predict the future. That's what LRU is about. And it seems like LRU would be a good approximation to min. The problem is, if you ask yourself, how do you actually implement LRU? It's not easy, right? Because, I don't know, you put all the pages in a list. And there's a head and a tail. And the tail is the least recently used, and the head is the most frequently used, okay? And most recently used. How would you implement this in an operating system? Somebody tell me why this is a bad thing to try to do. By the way, every one of you, I would expect, having gone through 61B, could build a list like this, right? Go ahead. Huh? Priority queue. Okay, how would you use a priority queue? So you would have to somehow, though, every time you use something, you'd have to get a timestamp and change all the other timestamps, or maybe? No, that's a good possibility. Keep thinking about that one. Yes?
I was going to say that with the priority queue, you could order it so that the lowest timestamp comes off first, and then every time you use a page, just update it to a new timestamp to be higher than all the others.
Okay, so you'd do a priority queue with some sort of timestamp, which is the most recent. Priority queue is worse than the linked list. I mean, well, how would we make the linked list work? Yeah.
Every time you use a page, you just basically pop it off and add it back to the head of the list.
Yeah, we'd yank it out of the middle, connect the list back up, put it at the head. Now, the important thing that people who have been talking have sort of glossed over is the every time you use the page statement. What does that mean? Every time you do a load or store, you got to somehow adjust this list. Right? So to do a load, you suddenly got to adjust this pointer to point there, bring this page out, put the head pointer, point on it, and so on. That's a lot. That's like 3 or 4 memory operations for every memory operation. And a priority queue is much worse. Okay? So this doesn't seem particularly good for a virtual memory system. Okay? And basically, we don't want to build this. It's too expensive. But what can we do that's similar? Yes?
Could we do like the access bit thing where, just like when you use a page and the page table entry, like set the access bit, and then like every so often like reset the access bits and like throw up or like invalidate pages that or I don't know.
Yeah. No. So basically, what we want to do is approximate LRU. Who said we need to be perfect? Do we need to know exactly the oldest page? No. What we'd like to do is divide the pages into old ones and new ones and reuse an old one. Okay, what you just described for me is actually the essence of the clock algorithm, which we'll talk about in a moment, which is you clear all the access bits for all the pages on a regular basis, and then if somebody uses them, the hardware sets the access bit, and that basically says, don't touch me, I'm a new page. And if you ever go and see the access bit isn't set, you say, oh, that's an old page. Okay, so rather than real LRU, which is too much information, right? We don't need this information. All we need to know is an old page, not the old page. Okay, and that's why I'm saying approximate. Okay, so let's take a break and come back, and then I want to really figure out what these different policies are. Okay. All right. Oh, we'll see whether my microphone makes it through the rest of the hour here. It's showing red. All right. So let's take a look at what the FIFO mechanism does. So suppose we've got 3 page frames and 4 virtual pages. And so 3 page frames mean we only have 3 physical pages of DRAM. So it's a very small system. And we have 4 virtual addresses we're dealing with. And the question is, if we've got this pattern, ABC, ABD, AD, CB, what happens? Okay, so let's take a look at this. So here are the 3 physical pages. We start by referencing A. When there's nothing in memory, so we're going to use FIFO, by the way, we'll start by mapping A into page 1. Okay, everybody with me? Now we do B. Where does B go to? Page 2. Okay, now notice that we don't mess with A, okay, because we're mapping in FIFO order. And so the last one is page 3, which is going to get C, okay? All right, so that's boring. So now what? What happens when we reference A? Page fault? No page fault, so A just works. Okay, what happens when we reference B? Okay, nothing. What happens when we reference D? Okay, now which page do we kick out? Okay, why? Because FIFO is the policy, right? Is everybody with me? What happens when we reference A? Okay, now we got to kick out B. Okay, so now here's a great example of why FIFO is a bad policy here, right? Because we kicked out A just before we used it. All right? D, what happens? Okay, good. B, what happens? Kick out C. C, what happens? Kick out D. B, what happens? Nothing. Okay? Okay, good. You guys are good. And so in the FIFO scheme, we actually got 7 faults on this particular pattern. Okay? Does that make sense to everybody? Now, you can see that when we reference D, replacing A here was a very bad choice. Maybe it would have better to replace like B or something. Or maybe even C, because C was the longest in the future, right? So min is actually going to do a better job here. Okay? So let's take a look at min. Same reference stream. Okay, A, which page? 1. Okay, now this first 3 things, who knows what min would do? It doesn't really matter because there aren't any pages mapped. Okay, so now we get to A. What happens? Nothing, right? It's a hit. B, hit. D. Okay, so here we're going to kick out C. Does everybody see why we kick out C? The reason we kick out C is because C is going to be used farthest in the future. Okay, remember, min is an optimal policy. Okay? A. Oh, it's a hit this time. D. Oh. B. Ooh. C. Oh, okay. Now, what do we kick out? Yeah, hard to say, right? We don't have enough future to know, but certainly kicking out A is okay because there's no A for the last guy, okay? And then B, we're good to go. So if we take the min policy here, we basically only have 5 faults. And where's D brought in? Well, we're always, basically we always look for C is going to be used farthest in the future, which is why we brought D here. Okay, good? Questions? Okay. What's LRU going to do? Well, what's interesting is it actually is going to do the same decisions as min. So if you take a look here, A and B are most recently used here. So basically C is the least recently used, so we'd kick it out. So notice here LRU is a perfect approximation to min. Okay? Questions? Now, when is LRU going to perform badly? Can anybody tell me? Yeah.
When we're looping over a set of data that's just too big for the...
Yeah. We loop over a set of data in a regular pattern. Look at this, A, B, C, D, A, B, C, D, A, B, C, D. Okay, ready? A, B, C, D, A, B, C, D, A, B, C, D. Okay, every reference is a page fault. Okay, so this is a great example where LRU just does the wrong thing. By the way, this is the same reference pattern that a fully associative cache might do very badly on. Okay, this is actually a pattern where a fully associative cache can do worse than a more limited associativity cache. Okay, and it's because basically on every axis you kick somebody out. So min does much better, as you can see here, on this same axis pattern. Okay, questions? So you can see where we're going here. So it's all about what do we kick out in this particular system, not what do we bring in. Okay, because since it's a fully associative page table, we can put the thing we bring in anywhere. So it's really about what we kick out. Now, here is an interesting graph, which is a hypothetical one. Wouldn't it be nice as we increase the amount of memory, the number of page faults should go down? People buy that? In general, right? As you increase the amount of memory, page faults should go down. Okay? Does this always happen? Okay, so the answer is no, but it seems like it should. Okay? And there's actually, however, something called Belady's anomaly, which says certain replacement algorithms, FIFO doesn't have the property that as you increase memory, the fault rate goes down, which is another reason to really dislike FIFO. Okay, and I have an example here. So does adding memory reduce page faults? Yes for LRU and min. No for FIFO, and here we go. So here is 3 pages and a reference stream. Okay, and you can kind of see where the page faults are. I didn't colorize this, but you got the picture. Here is 4 pages, and now there are more page faults. Okay, and so basically, with FIFO, the contents, the real issue here is that with FIFO, these contents here and here are completely different from each other. Whereas with LRU and min, as you add memory, the memory that you started with will continue to look pretty much the same as part of the memory you added to. Okay, so here we've got 4 items. At least 3 of them would look very similar to the 3 if we had LRU or min. Okay, so this is another reason to dislike FIFO, because it can run into Belady's anomaly here. Okay. So let's implement LRU. So perfect implementation is complicated. Maybe we timestamp the page in every reference. We keep a list of pages ordered by time, and we pull the oldest page out. Okay, now that's just not doable in hardware. So here's the typical algorithm to do this, called the clock algorithm. And remember, we're going to approximate min, and LRU for that matter, by finding an old page, not the oldest page. That's our goal. So how do we do that? So hardware has what's called a use bit in the PTE. We showed you that before. And what happens is anytime you reference a page, the hardware sets the use bit. And if the use bit isn't set, then you can conclude that this page hasn't been referenced since the last time you cleared the use bit. Okay, so now basically we've got an algorithm. We go through, we clear all the use bits, and then we go back and we look at them later, and if the use bits are still off, we say that's an old page. Yes? So there's 1 use bit per page table entry. I'm going to show you some variants on, no systems implement more than 1 use bit that I know of, because it's basically used or not used. But then by using extra software, you can do more. Yeah, and I'll show you some options here where 1 use bit can still give you a better flavor for how far used in the past. Because as you see right here, I'm kind of dividing into 2 pieces, and we can divide into some more subcategories in just a second, but 1 use bit still. Okay, good. So Nacho's hardware actually sets the use bit in the TLB for you, so that's good. The downside now is that TLB entries are potentially dirty and may need to be flushed out to memory before you replace them. Okay. So what happens on a page fault? Well, we've arranged all of the physical pages in a big circle, which is a clock, right? And we have a clock hand that's walking along. And on a page fault, what we do is we advance the clock hand. We look at the next item, and we say, gee, is the use bit on or not? If it's off, we say, oh, this is an old page, we'll use it. If it's on, we say, well, it's been used recently. I'm going to reset the use bit and go on to the next page until I find one with the use bit off. Now notice I simultaneously checked the use bit and then cleared it. And so as we walk our way around all of the physical pages, the hand is both clearing the use bit and looking at the use bit at the same time. And so the use bit always gets cleared once per loop. Okay? And, 1 basically means used recently, so clear it and leave it alone. 0 means it's a candidate for replacement. And can we always find a page, or are we going to loop forever? You can imagine that all the pages are being used, and I clear, and I just never find anything free, right? So there's a version of this algorithm that you could imagine thinking went forever. However, the way this algorithm's usually spec'd is you stop all else, and you're walking your way around until you find something clear. So if worse comes to worse, by going one full loop, you will always find one clear, because nobody's running while you're looking. Okay? Now, we'll make that more efficient in a little bit. But any questions on this idea? Yeah. Well, the way I've spec'd it here, the clock algorithms run every page fault. So basically, you only advance the hand when you need pages. And if you're not advancing the hand, you don't need pages, why touch anything? Okay? Question, yeah.
How do you deal with the arranging of the physical pages in hardware or software?
Well, the arranging of the physical pages is all handled in software. So you could imagine a big linked list is made at the very beginning of time when you boot. Or, since you could view memory as a huge array, you don't even have to build a linked list. You could just have an index that went through. You probably link a list in I'll show you why in a moment, because you want to have a free list also. But this is a simple version of the algorithm. So there it is. It's a clock. Okay, and this one's a little bit off, but close. So what if the hand is moving slowly? Good sign or bad sign? Good sign. Not a lot of page faults. Yeah. What if the hand is moving quickly? Well, you're in trouble, right? First of all, it means that you're probably page faulting a lot. And secondly, if you're moving past a lot of things, it means there's a lot of use bits on before you find a free page, and so there's a lot of pages in use. So the hand moving quickly is probably a sign that you're under memory pressure and you're probably paging a lot to disk. Okay? So the way to look at this is it's a crude partitioning of pages into young and old groups. Okay? Now, before I go on to some variants on this, does this make sense to everybody? Does anybody have any questions on this notion of partitioning into two pieces, old and new? Okay? So, here's the nth chance version. Okay? So we want to give a page n chances. Okay? So what does that mean? Well, the operating system is going to keep a counter per page. And on a page fault, the OS checks the use bit. If it's a 1, we know it's been used recently, so we just clear the use bit and the counter, and that is a recent page, no question about it. What's more interesting about this is what happens if we hit a 0. In that case, it's an old page, but now we want to know how old. And so what we do is, on 0, we increment the counter, and if the count is equal to n, at that point, we throw it out. Okay, so what we're going to do is, before we kick out a page, we're going to give it n loops of the clock before we finally kick it out. Okay, that's why we call it the nth chance. And so how do we pick n? Well, if n is really big, you actually get a better approximation to LRU. Okay, at the cost of, what's the biggest cost here? Yeah, the biggest cost is not, by the way, the little counters on the PTE. The biggest cost is to find a page you're probably looping many times. Okay, so potentially there's a lot more motion on the clock here. So why pick a small n, more efficient? Okay, so here's an interesting use of n. So what about dirty pages? So we've talked about the use bit. There's also the d bit. What do we need to do before replacing a dirty page? Write it back to disk. So here's how we could use n. So it takes extra time to replace a dirty page. So what happens if, when we see a dirty page, we start it out to disk, but bypass it? So when it's dirty, we pretend that n is 2. And when it's clean, we have n equal 1. Okay? So this is basically, as we're going around looking for pages, if we see a candidate page and it's dirty, we write it back, start it writing back to disk, and we keep going. And if we come back to it later and it's still not in use, it's been written out to disk, and we can now use it. Okay? Questions on the nth chance? Yeah.
What if you're not able to find any page that's old enough to replace?
Well, what's going to happen here is eventually, you could circle many times, and finally, every time you go around, you're aging the pages, so you'll eventually find one. Because we're not letting any accesses go on during this process. So, which bits of the PTE are useful? Well, the use bit is what we've been talking about. The dirty bit or modified bit lets us know what to flush out. And then, of course, there's things like valid and read-only, which we've already decided are useful for other parts. Okay? So do we really need the modified bit? Okay? You might say, well, wait a minute. If I don't know that the page was modified, then I might overwrite it without saving the data. Well, the way you can get by without the modified bit in hardware is every time around the clock, you mark the page read-only. And if somebody tries to modify it while you're going around, you page fault, mark your little software bit, and then you mark it read-write. And so by the time you get back around to it again, you have a software bit that says dirty. Okay, so by playing with the read-write bit and turning it off, I can find whenever you do a write, because I'll get a page fault. Okay, question, yeah.
You actually want it to be read-only?
So how do you distinguish between actually read-only and temporarily read-only pages? Good question. How? Presumably, there's some other data structures the operating system's keeping, right? And in fact, if you take a look at the Intel PTE, there's actually 3 bits that you can use that are for OS. So they are totally not interpreted by the hardware, so you can use them any way you want. Do we need a hardware use bit? How do we emulate the actual use bit if it's not in hardware? Anybody? Similar to what we just did for the dirty bit. Go ahead. So,
You mark it read-only, and whenever it's
well, but read-only doesn't quite do it for you. Yeah. Go ahead.
you could mark it invalid when someone reads it.
You mark it invalid. So instead of clearing the use bit, what happens is you mark the page invalid when the clock hand comes around, and the moment somebody tries to use it, you get a page fault. You mark the fact that it's in use, and you've got now you set it to read-only or read-write, whatever it is. Okay? So basically, we can emulate pretty much these. We don't need use and dirty at the expense of some extra page faults. And it's kind of so it's kind of funny, by the way. So this is just saying what I just did. But the clock is just an approximation to LRU, and so we might ask ourselves, if we're going to page fault on use and dirty bits, maybe there's a different approximation to LRU than the clock algorithm, because the clock algorithm's really developed to have a hardware use bit. I mean, we can get by without the hardware use bit, but the clock algorithm was really developed for the hardware use bit. And this is, by the way, a funny thing. The VAX, which is a well-known, yeah, question.
Why would you ever want to get rid of one bit if it causes more page faults, which slow down your operation?
So, question, why get rid of a hardware bit that seems so useful? Answer, You remember the VAX, which I kind of made fun of early this term as the thing that had polynomial multiply? Okay, now it's not really fair to make fun of an architecture that everybody used. I mean, it was the mini computer, everybody had one. What was interesting about the VAX, several of the VAX architectures was that Strecker, who was the chief architect, came to the operating systems guys and said, what do you need from me? Do you need, and he started asking things. Do you need a use bit? Nah, we don't need a use bit. Okay. Now, unfortunately, later, it turned out they really could have used the use bit. Okay, and so they had to develop algorithms for dealing without the use bit. Okay, so you probably would put it in there if you had your option, but if your poor hardware guy has been misled into not putting it in there, then you got to figure out what to do. Okay, and I'm not going to go into this. I'll go into this more next time, but let me show you for the VAX, they actually developed called the second chance list algorithm, and we'll talk about this next time. The idea here is the green pages here are directly mapped read-write. Okay, so the hardware never gets page faults here. The yellow ones are managed LRU in software and always get page faults because they're marked invalid. And so the idea here is if you access any pages over here, they go full speed. Okay, and nobody knows the difference. Otherwise, you get a page fault because these are invalid, as are the ones out on disk. And now what happens? Well, when we get a page fault, we're managing this FIFO, so we're going to take the extra one that's the oldest from a FIFO standpoint and put it in our LRU. We're going to grab the one that we wanted that's page faulted if it happens to be over here, and we're going to put it in our FIFO list. Otherwise, we may have to bring it out off the disk, and so we'll put something in off the disk. Okay? Now, I'll talk about this next time, so don't worry about the fact that I'm going fast on this. But if you look at what's going on here, is we have some pages that are being managed FIFO, but they're mapped full speed, and the other ones are actually managed LRU, and the net effect is a pretty good approximation to LRU. All right, we'll talk about this next time. So in conclusion, precise exception specifies that there is a single instruction for which all previous instructions have completed and no following instructions nor the actual instruction have started. We talked about several page replacement policies, FIFO, min, and LRU. And we gave you the clock algorithm, which is, by the way, some variant of the clock algorithm is pretty much in almost all operating systems today that page. We started talking about the nth chance algorithm. And next time, we'll actually look at another. We talked about nth chance, and we'll finish up second chance next time. All right. Good luck. See you guys on Wednesday.